Okay. These sections, we're going to look at fundamentals of Ethernet LANs and WANs. We're going to look at physical and data link layers for local area networks, and also physical and data link layers for wide area networks. Now, physical and data link layers for local area networks, we have local area network. Part of that, we have UTP cables. Some of the types of cables we are using, such as straight-through and crossover. We have some a device, and that device transmit the pin pair. Then LAN data link layers, Ethernet addressing, half versus full duplex, CSMA/CD. These are the things they are related with our local area networks. Now let's have a look. Now, let's say we have one small network. We have a switch. We have some PC connected in here. We may have some server connected in here. And we have wireless access point. Then we have some wireless devices in our network. So all of the device, they are connected with switch. Let's see. Right, this is PC1, PC2, this is PC3. This is maybe one of the server, this is maybe Active Directory, or this is maybe wireless access point, right? And you can see all the devices in our network, they are connected with switch. And wireless device, they may connect with the wireless access point, but wireless access point also connect with the switch. So switch is the main connector. And in our network, we can have router as well. And router provide us many things, but one of the things they provide us outside connectivity, internet connections or wide area network connections, those kind of things they provide. So this is one of the local area network. Local area network, it could be one office, it could be one building, or few buildings in a closest geographical areas. Now let's say this is Sydney LAN. And this side, we may have another LAN. So this is maybe from Melbourne. We have some switch here. We may have some other devices connected. So those devices, they are connected with this switch, and switch connected with the router. So that's another branch office or head office located in Melbourne. So we call it Melbourne LAN. It's short, Melbourne LAN. So you have a Sydney local area network and Melbourne local area network. Two offices we have in two different locations. And if you'd like to connect these two offices together, the private connections, that kind of scenario, we need wide area network connections or WAN. Let's say we have ISP in between. ISP can provide us this kind of wide area network connectivity from source to destinations, like that. This is router 1, router 2, like that. So they are ISP. This is the two different locations we have. And to local area network, we can connect with wide area network. But these days, there are many other alternatives to WAN. Like let's say we have VPN connections, and there are some other types of VPN and WAN connections also available. But main thing is this is private link. Private link, that's the private connections from two different locations. That means whatever connectivity ISP providing to these offices, they will be private. They will not be shared with other people. So wide area network managed and maintained by ISP, and we have to pay for that network. But local area network, you can manage by yourself. All the device, their connectivity, everything locally you can manage. Now, these are the two areas we're going to look at how our OSI, physical and data link layer, they are related. Now, let's have a look physical and data link layers for LANs. LAN physical layers, we have different physical standards. So that means we have copper wires, fiber wires. In our network environment, we can have maybe Ethernet connectivity or Ethernet cable. Ethernet cable, there looks like this. They are called RJ45 standard. So we have a switch as well. Switch also, switch port, they are RJ45. That means this Ethernet cable head, it will go over there. So mostly in our network, we can have Ethernet cable or copper cable, or in many contexts, we can have fiber connectivity as well. This is the two different medium we are using in our network. Now, LAN physical layers. So we have switch 1, switch 2, and switch 3. And we have some PC, let's say PC1, PC2, PC3. Switch 1 and switch 2, we can see we have the connectivity with fiber cable, which is 1 Gbps. Switch 2 and 3, we have connectivity with fiber cable, 10 Gbps speed, and distance is 1 kilometer. But end user device, they're connected with switch with UTP cable. UTP stands for unshielded twisted pair. They're kind of like a Ethernet cable, copper cable, we can say. And this one support 10 Mbps. This one support 1 Gbps UTP cable. This one support 100 Mbps UTP cable. So these are the devices they're connected with switches, and you can see end user device they connected with copper cable. But usually when device to switch to router or switch to switch, those kind of scenarios, we are using fiber cable. Fiber cable comparatively, they're better than the copper cable in terms of like transmitting the data, providing bandwidth, and especially distance. If you have long distance, then the options is the fiber, because our copper cable support maximum distance up to 100 meter. So if you connect a cable from your PC to switch, maximum distance it will support 100 meter. But fiber, they support like, let's say 200 meter to 1 kilometer, and few cases like 40 kilometers, 50 kilometers, and long distance, it supports that types of connectivity. Now, straight through versus crossover cable. Straight through cable, we have these types, let's say PC to hub. PC to hub, we have connectivity. We can see inside this straight through cable, we have 8 different pairs or 8 different pins, we say. So that means 8 different cables. They're like a very thin cable. Inside this unshielded twisted pair, like this is a unshielded twisted pair. So inside this cable, we have 8 different pins. These are the pins. Some of the pins used for transmitting purposes, some of them using for receiving purposes. They transmit and receive signals. This is their main job. Now, straight through cable, pin number 1 and 2, one side they do transmit, and the side they do receive. And pin number 3 and 6, one side they receive, and the side they transmit. And crossover cable, one side they transmit, and the side they receive, but receiving in pin number is 3 and 6. And this side, pin number 3 and 6 using for receiving purposes, and the other side, 1 and 2 is for transmitting purposes. So the difference is pin number 1 and 2, they actually ended up on the other side in pin number 3 and 6. And also 3 and 6, they turn to pin number 1 and 2. That's the crossover cables we have. So why we have straight through cable and crossover cable? Because different device, they transmit and receive the signals in different way. So if you have a PC and hub, PC is sending via pin number 1 and 2, hub and receiving pin number 1 and 2. But if you have a PC to PC, because PC is sent via pin number 1 and 2, on the other side, that's why they have pin number 3 and 6, which can receive the same information. Because same type of device, that's why we should use crossover cable. Again, pin number 3 is receiving, and pin number 1 and 2 is sending. So same types of device, we should use crossover cable, and different types of device, we should use straight through cable. So that's why different device, they have different kind of transmission capabilities. Let's say PC, NIC card, routers, wireless access point, they transmit on pin number 1 and 2. On the other hand, hubs, switch, they transmit on pin number 3 and 6. So they transmit on pin number 1 and 2, and then this transmit on pin number 3 and 6. In this way, when this PC wants to send some information to this switch, PC will transmit via pin number 1 and 2, and switch will receive that info, and then switch will send back to 3 and 6. In this way, transmit and receive, these things going on. Now cabling, straight through, we have different sort of connectivity. So, and crossover cable, we have this kind of connectivity. Now, different types of device, we should use straight through cable. Remember this one. Let's say switch and router, switch and PC, switch and server, hub and PC, hub and server. And this side, like let's say same types of device, switch to switch, switch and hub, hub and switch, similar sort of device. So when you connect hub and switch, hub to hub, router to router, router and PC or PC to PC, so they are all these are the scenarios we're using crossover cable. So you can straight through cable, and we can use crossover cable in this way. Only exceptions, we can see that router and PC, they are different kind of device, but still we are using crossover cable, because many context, PC can be working as like a router as well. They can do a bit of routing as well, many context, PC or server. That's why this kind of connectivity, we can use crossover cable. So easiest way to remember these stuffs, same types of device, crossover cable, different types of device, we should use straight through cable. Usually these days, there's a auto negotiations enabled. So device, they can negotiate and they can communicate, but still in many contexts, this cable connectivity can cause problem as well. So you just need to remember this one. Now straight through versus crossover cable. You can see same types of device, all the switch using crossover cable, but different types of device we are using straight through cable. They're all like copper cable or Ethernet cable. They have many name and brand, but internally, that's how they functions. Now, cable standard. So this is the speed we have: 10 Mbps, 100 Mbps, 1000 Mbps, like the 10 Gbps. So these are the speed we have in our network connectivity. Like 10 Mbps, common name Ethernet, IEEE standard name 10BASE-T, formal IEEE standard name 8023, and cable type copper, maximum length or distance they support 100 meters. Any copper cable you can see, maximum distance they support 100 meters. Now 10 Mbps, fast Ethernet, 100 BASE-T, 8023U copper cable, we can run up to 100 meters. 1000 Mbps, gigabit Ethernet, 1000 base LX, 8023Z, different standard. And this is a fiber cable, we can run up to 5000 meters. But different standard of fiber cable, you can run up to 1 kilometer, 10 kilometer, 50 kilometer, like that as well. At same speed, if you have a fiber, if you have a normal Ethernet cable, then copper cable, you can run up to 100 meters. 10 Gbps, 10 gig Ethernet, we can run up to 100 meters. So these are the physical standard we have, cable standard we have. And when you do network connectivity, during that time, we need to choose the correct cable, correct specifications. And after that, we should be able to configure the network. Now, data link layer, how data link layer, they are connected with our physical layer. Single data link layer is standard for different physical layer standards. Ethernet data link protocol defines Ethernet frame, Ethernet header at the front, data will be in the middle, and Ethernet trailer will be at the end. That's how in layer 2 or data link layer, a frame built. So inside the frame, we have header. Inside the middle sections, we have packets, and at the end, we have Ethernet trailer. In the header, we have some informations. Let's say preamble. Preamble maintain the synchronizations with another frame. SFD stands for start frame delimiter. This one actually introduced the destinations MAC address. And then we have source MAC address. So that means in one frame, we have destinations MAC address informations, source MAC, like where this frame came from, that information's type field, whether IPv4 or IPv6 packets, that information will be there. And then data will be inside here, these sections. And maximum data, it supports 1500 bytes in one frame. And this side, we have a frame check sequence, FCS. Frame check sequence will ensure that this frame is error-free. There's no issues with this frame. And you can see one thing, in one frame, we can have only 1500 bytes of data. That is called MTU, maximum transmission unit. So one frame contain only 1500 bytes of data. That means if you send 5 meg file or 10 meg file, during that time, switch will create many frames. There will be many frames. And one frame will synchronize with another frame. So all the frame, they will continuously synchronize with other frame. One frame, two frame, three frame, all the frame, and they will sync with each other. And at the end, when you try to open, all the frame they will bind together and produce some file format. So one frame can contain only 1,500 bytes of information or data. So that means if you send more files, a lot of files, that means in the back end, our switch is creating many frames. Usually, we do not have to do any troubleshoot with these frames, but we need to know that in the back end how frame functions. And usually, majority of the switch and their ports, they support this kind of like frames, 1,500 bytes, but some of the switch, they support jumbo frame. So that means they support more than 1,500 bytes, let's say 1,600, 700, or 800, something like that. Whole 7 bytes, it's maintain the synchronization. SFD, 1 bytes, and it signifies that next byte begins with destination's MAC address field. Destination's MAC address will be 6 bytes, identifies the intended recipient of this frame. Source MAC address, 6 bytes, identifies the sender of this frame. Type field, we have 2. IPv4 or IPv6 packet types it defines. Then data field, we have data informations like minimum 46, maximum 1,500 bytes it can hold. And frame check sequence provides a method that receiving need to determine whether the frame experienced transmission errors. So these are the informations will contain in one frame, but we'll have many hundreds and hundreds frame always coming and going from our switch. Ethernet physical addressing. Ethernet address, physical address, MAC address, they are actually referring to the same thing. But mostly we know them as MAC address, used for LAN communications. So MAC address, they are 6 bytes. So 3 bytes used for original unique identifier, and another 3 bytes used for vendor informations. So broadcast MAC address for LAN. So that means we do broadcasting in our local area network with this MAC address. MAC address written in hexadecimal format. Usually it looks like this: 00602F3A07BC. They are the MAC address. And 1 hexa equal to 4 bits. That's why 6 hexa equal to 24 bits, or 1, 2, 3, 4, 5, 6, 6 hexa, and 6 hexa equal to 24 bits. And also another thing we need to know, like 1 byte equal to 8 bits. 1 byte equal to 8 bits. And in the MAC address, we can see that we have here originally unique identifier. This is OUI. And this side we have a vendor assigned. We have a NIC cards and interfaces. This side we have vendor assigned. So OUI, this is mostly for original unique identifier, and this side we have a vendor assigned. This is mostly saying that unique identifications, unique ID. So MAC address will contain unique ID, and another part it will have a vendor informations. That means it's from Dell, HP, those informations will be in the second part. That means by looking at the MAC address, we'll be able to see the vendor information as well. And MAC address will be unique all over the world. So that's why when they assign this MAC address, they need to follow, standard from IEEE, and that's how MAC address assigned to particular devices. And MAC address, remember, is bind with actually NIC card. NIC means network interface card. Whether you have a PC or if you have a laptop may have wireless network interface card, or we call it Wi-Fi. Actually, that is a Wi-Fi NIC card. And that NIC card will contain this MAC address information. So another thing we have called half duplex versus full duplex. So network communications, full duplex means communications will take place both way same time. That we call it full duplex. And communications happen when communications happen in one way at a time. This is, we call it half duplex. These days, majority of our devices, they support full duplex, but hub, this is old device, and hub only support half duplex and 10 Mbps speed. We are not using much hub these days, but maybe some legacy network, you may find hubs over there. But if hub is over there, so that supports only half duplex communications and also 10 Mbps speed. Now, another technology they're related with this hub, this is called CSMA CD, Carrier Sense Multiple Access with Collision Detection. Let's say we have Larry, and this side we have Archie and Bob. If Archie and Bob want to send some information to Larry, these informations may collide. And when they collide, then there'll be some issues. That's why we have this CSMA CD. So this technology actually stop these collisions and send one informations at a time. In this way, they can avoid the collisions, but the communications will be very, very slow. That's why hub support only 10 Mbps and also kind of like a one-way communications, which is called half duplex.